Before we begin investigating acids, bases, and pH, I want you to take a look at some of these strong acids and see if you can figure out what they all have in common. Okay, if you clued in on the fact that they all have these hydrogens, congratulations. Hydrogen is going to be our focus as we continue on in our discussion of pH. We'll get back to these acids. Now, water at any one time will always have a little bit of its ionic forms present. So this is called the self-ionization of water, where the hydrogen ion and the hydroxide ion will spontaneously form. Now, it's a very, very small amount of these two ions that will form. Now, more correctly, hydrogen ion, once it's formed, will immediately bond with a water molecule to form hydronium ion. So the equation below is more correct. We're going to continue to talk about just the hydrogen ion and the hydroxide ion and its role in pH to keep it simple. So acids are substances that increase the hydrogen ion concentration of a solution. Anything that increases that hydrogen ion concentration. Bases are exactly the opposite. Anything that increase a hydroxide ion concentration or lower the hydrogen ion concentration. So understanding acidity is really all about understanding what things affect the hydrogen ion concentration of a solution. Acids are substances that will dissociate in water and raise the hydrogen ion concentration. So if we take a look at hydrochloric acid in water, then we know it will dissociate into that single proton, a hydrogen ion, and chloride anion. So see if you can go ahead and write out the rest of these reactions in water, the ionization of nitric acid and sulfuric acid. Okay, hydrogen ion, of course, will form since it's an acid, and then the nitrate anion is left over, the conjugate base to the hydrogen ion. And sulfuric acid, we see there's two hydrogens in sulfuric acid, so two hydrogen ions are formed, and then those two hydrogen ions are balanced by a -2 charge on the single sulfate molecule. For the bases, same exact system here. We're dissociating in water, this time raising hydroxide ion concentration. So sodium hydroxide then would form the sodium cation and the hydroxide anion. Again, pause the video for a moment and see if you can complete the formulas for potassium hydroxide and calcium hydroxide. Potassium hydroxide will dissociate into, just like with sodium hydroxide, the potassium cation and the hydroxide anion. Now, calcium hydroxide, you see there's two molecules of hydroxide in that single molecule, and those two negative charges provided by the hydroxide ions must be balanced by a +2 charge on the calcium. And you can check back, do an orbital diagram for calcium. You see it's atomic number 20, and you'll see that calcium has two valence electrons it likes to get rid of, thus giving it a +2 charge. The pH scale runs from 0 to 14, with smaller values indicating more acidic solutions, which of course is increasing the hydrogen ion concentration, and numbers closer to 14 are basic solutions, increasing the hydroxide ion concentration. Neutral pH is 7, and what that means is that the concentrations of hydrogen ions and hydroxide ions are exactly equal to each other. So here are some common substances and where they fall on the pH scale. Notice hydrochloric acid up there at the top, a strong acid at 0, and sodium hydroxide, a strong base, down at 14. Now that pH scale is a logarithmic scale, and it's exactly a measurement of the hydrogen ion concentration. And logarithmic means that each difference in pH unit is a tenfold difference in hydrogen ion concentration. So hydrochloric acid up there at 0 is actually 100 times the concentration of hydrogen ion than lemon juice at 2, and 10,000 times the hydrogen ion concentration of tomatoes at pH of 4. pH actually stands for the negative log of the hydrogen ion concentration. So if you take a look at these different concentrations up at the top, I want you to notice the first one here. Now remember, we said that at any one time a very small amount of those ions had formed in, say, a glass of water. So look at this concentration, 0.000001. Now it's very cumbersome to express a concentration in that way. So what we use is something called scientific notation to express that very small number. So if we take the number 1 there at the center of the screen, 1.0, and we wanted to make it the first number that I have outlined in red there, what would we need to do? We would need to add all of these zeros and move that decimal 6 places to the left. Now that number is exactly the same as saying 1 times 10 to the negative 6, because we had to move that decimal point to the left 6 places. Now, the log of 1 times 10 to the negative 6 is simply the exponent on that number 10, negative 6. Therefore, the negative log would just be the number 6. And therefore, that's how that concentration of 0.000001 moles of hydrogen ion per liter gets transformed into a pH of 6. Now you can see how as we increase the concentration, so moving up there from arrow to arrow, we are getting a bigger and bigger number. That means that we get a decrease in pH as a result of that negative log relationship. And therefore, an increase in acidity is a decrease in pH.